So let's look at this table of transforms then and try and relate it to a circuit and some components. If we have an electric circuit, so let's make one up. With a capacitor in it and some sort of voltage, and we're going to use a step voltage of 10 volts and a resistance of say 20 ohms and a capacitance of 10 farads. I know it's a little bit big, well let's start off with some small numbers. By the way, you have my permission if I ever write down a number 5 as an example, just tell me to stop and I'll change it, okay? And the reason will become obvious as we go along why 5s aren't a good idea to use for examples, because they look like S's, yeah. And we're going to be working in S space, so we've got S's and 5s and S's and oh my god. So I'm going to try and avoid them. So we have a circuit that's involving a resistor, a capacitor and a voltage. And what we're going to do is try and find out the current. What does that look like in this circuit? And the current, well, we've got to start off. The current equals the voltage over the resistance. So I'm going to apply Ohm's law, I equals V over R in this circuit. But what I want to do, because this is an instantaneous current, in other words, it's time dependent, it's changing. And so actually, it's a moving feast and we need some sort of function that's a changing function, i.e. a differential equation, so we're going to use Laplace transforms. It's not as straightforward as just using Ohm's law. For this transient period, at the instant I turn on the circuit, things are going to be changing, and during that period, what's happening? Let's have another little guess. I don't know how well you did on the last guess, but sketch a set of axes, and what do you think will happen in this circuit? And think about what the current will be at steady state, and then what might happen as we get there. What's the initial current, and what happens to that current until it reaches that steady state? So I'll just pause this for a second while you think about that and sketch something. Okay, here's the overall method. What we're going to do is we want the voltage and we want the resistance. What we need then is to transfer this voltage into S space using a Laplace transform. So we look at our table of transforms and we look at what we do with supply voltages. Look, here's a component or the voltage or a step voltage. We're going to transform that into something in this thing called S space. And then we're going to take our components, our resistance and our capacitance, and transform those into S space, manipulate them until they look like one of the components in our table, and we'll talk about that more when we get to it, and then transform it back and see what we get. That's the idea. So the initial step is to take our components and transform them into S space. So we have the voltage as a function of time equals whatever that is from our transforms. The resistance of the resistance component as a time component, what does that become? And the capacitance, what does that become? So from our table, we have the resistance. Say we had a resistance of 10 ohms. So the resistance, what happens to the resistance? It, in S space, is exactly the same. R stays as R. So a 10 ohm resistor stays as a 10 in S space. A capacitor, though, becomes 1 over C times S, where S is this S space. So if I have a 4 farad capacitor, this becomes 1 over 4S. So we just use our table to transfer this into this new thing called S space. It's just a mathematical trick to allow us to avoid having to do integrations. And the 10 volt supply becomes V over S, so 10 over S. So we can use our table to write down what each of these things is. No, for a step it was just over S. Yeah. So the voltage becomes 10 over S, should be a 10. The resistance becomes just what it was before, which is 20. And the capacitance, which was 5, no, not 5, 10, becomes 1 over 10S. Now we've got a resistor and a capacitor in series, so we can effectively add them together. The total resistance effectively is 20 plus 1 over 10S. So we can add those in series. We can, once transferred to S space, we can think of these just as values. We don't need to think about, oh, I can't combine the resistance of a resistor and a capacitor because they're out of phase. We're not thinking about things like that. So it's not effectively combining resistances. This is now in S space, this new dimension which allows us to do this. No, they're transforms, yeah. So the current in S space, because we transform now, is a voltage which is 10 over S over 20 plus 1 over 10S. If you now look at your table of transforms that you've got here, what we want to do now is to try and get our answer to look like one of these so we can transform it back. The problem is it doesn't look like any one of these. If we look at our solution we've got so far, here, it's a bit of a mess really, okay? For a start off, if we look at our table of transforms, only S. If we look at any of these on the right hand side here, it's just S squared, third one down, S squared plus A squared, and so on. So the first thing to do is to try, when you've got a situation with 10 over S or 1 over 10S, as we've got here, is to try and get, if possible, the S on its own, particularly underneath. And so we start using little algebraic tricks. First of all, I don't like this S being underneath on the top here. So I could multiply top and bottom by S. If I multiply top and bottom by S, I can do things like cancel out those S's and so on. So it's little tricks like that that we do to try and simplify it. So, and that is just going to come with practice. You're going to need to practice doing that sort of thing. So we might decide to multiply top and bottom by S. And we get 10 over 20S plus 1 over 10. This already looks a little bit better. 10 over 20S plus 10. I've got some term, some number on top, some term involving S on the bottom, and another term. And if we look at our table of transforms, then the second one down, or the, looks similar, look, okay? This one. What, a term on top, a number on top, and an S and another number by the side of it. So we're on our way. What we're after now is to try and get this to look like one of those. Well, the next thing to recognise is that this S is not on its own. It's got a 20. So what can I do to get rid of that 20? Not times, because I want to get rid of it. If I divide by 20, I'll get rid of it, won't I? Divide both sides, both terms, top and bottom, every term, in other words, by 20. So that would be my next step, divide by 20. 10 divided by 20 is 0.5 over 20s divided by 20 is just s, and 1 over 10 times 20 is 1 over 10 times 20, which is 200. Divide all terms top and bottom by 20. So IS equals 0.5 over S plus 1 over 200, which is as a decimal 0.0. 201 goes 0, 209 goes 0, 200 goes 0, 1000 goes 5, 0.005. Pardon? Ah, sometimes you just can't avoid them. So it's 0.5 over S plus 0.005, having gone out my way to avoid 5s. Look at our table. It looks like the second one down in our table. Okay? So from our table, it looks a bit like this one. Does it not? Okay? Let's look back at our final result and rewrite it over here so we can see it. IS equals 0.5 over S plus 0.005. Making every attempt to make my 5s look 5 and my S's look like S's. And now we can compare that with this. E to the AT equals 1 over S minus A is the transform that we're using. What this is saying is, in S space I've got this, but in converting back to reality, if you like, to time, it looks like an exponential function. And A in the function we're after is this number here. So in our case, A is 0.005. And in the transformation, if this is a minus, then it's positive, e to the plus AT. So presumably, if this is positive, then that will become negative. So to make the transform, what we do is we say, therefore, 0.5, one bit to think about yet. What's that? What's the other difference between what I've got here and what this is? The 1, yes, that's a 1. Oh yeah, that's a 1. And so, what can I do about that? Sorry? If I times top and bottom by 2, I'd have a 1, wouldn't I? Because 2 times a half is 1. But then I'd have 2s. I can separate it out. I can think of this as being 0.5, I'm in the magic pen mode, 0.5 times 1 over s plus 0.005, can't I? I can separate that out. And so we have 0.5 times 1 over s plus 0.005 equals 0.5 e to the minus 0.005 t. So let's just recap this. We've taken a circuit. We've taken our components in the circuit and transformed them into S space. So a 20 ohm resistor looks like 20 in S space. A 10 farad capacitor becomes 1 over 10s in S space. And then I add them together because they're in series, 20 plus 1 over 10s. what does the voltage become if it's a step voltage? 10 over S. And then I apply Ohm's law. I equals V over R, effectively. And then this is the algebra, this is the tricky bit. I manipulate it. I times top and bottom of this by S to get rid of that fraction that's in Vs there. And that automatically gets just S on its own here. And then I divide by 20 to get rid of this 20 there. And then I end up with this. And then I look in my table of transforms for one that looks like that. And then transform it. And I end up with this. And this now is our function back in time again. So in other words, IT equals this, 0.5 e to the minus 0.005 t. And the board's going off sync again. I can plot that on autograph. Y equals 0.5 e to the minus 0.005 t. Let's do that. And we get this. That is our prediction, our model for what's going to happen in this circuit when I turn on the supply, that step voltage. I can put values on it now. It's predicting that the initial current will be 0.5 amps. And that it will take around about, well, greater than 400 seconds for the current to drop to a steady state, which is 0. Let's apply that back to our original circuit and think about the guess you made for the circuit. If we look at it, at the instant I turn on this supply, 10 volt supply, with the capacitor initially discharged, we can effectively ignore the capacitor, can't we? And so the current is just V, which is 10, over the resistance, which is 20, a half an amp. So that's borne out by that graph. I could have predicted I'm going to start off with half an amp. What I can't predict is how long it's going to take for that to drop to 0, but that's what this is telling me. With that particular circuit, with a large capacitor, a 10 farad capacitor, it's going to take a long time for that capacitor to, for the capacitor to fully charge and for the current to drop to 0. So we've come up with a way of working out the transient period for a circuit involving a capacitor and a step input DC.